Hello everyone, we are a research team from King's College London. Today, we are pleased to present our project titled Wireless Split Federated Learning between the edge server and XR devices. This work focuses on collaborative learning between edge servers and extended reality, XR, devices, aiming to improve the efficiency and privacy of federated learning in wireless network environments. We introduce the background and motivation for our work. With the emergence of 6G AI-native networks, there's growing interest in split learning, SL, under wireless environments. However, this introduces a fundamental trade-off between computation and communication, especially when training deep models across XR devices and edge servers. Our motivation stems from several challenges. First, there is no standardized testbed to evaluate such systems. We aim to provide a system-level evaluation using Smart Edge opEn together with SDR and the OAI platform. This allows us to study the impact of the split layer, as well as critical system metrics such as accuracy, latency, and overhead. Ultimately, our goal is to advance edge AI technologies for future 6G networks. On the left, we have a GPU server running the edge-side split learning model. It handles the heavy computation tasks and coordinates with the user device over a wireless link. At the center and right, you can see two USRP devices, one acting as the server-side radio and the other as the user-side radio, user. These are used to establish a real-time wireless connection using the OpenAir interface stack. The small black box on the right is the CPU-based user equipment, CPU-UE, which runs the client-side model and transmits intermediate data to the server. The neural network architecture we used for split learning and the cutting strategies we evaluated. The model follows a PointNet++-like structure, processing 3D point cloud inputs on the user device. We designed several cutting points, from Layer 1, FP1, to Layer 4, FP4, where the model can be split between the user and the edge server. Each cutting point results in a different output tensor size and computational load. As shown in the table, earlier cuts like FP1 reduce the user's computation but increase communication load, while later cuts like FP4 shift more computation to the user but reduce the size of the transmitted data. This slide illustrates our end-to-end system setup and its runtime environment. We implemented a 5G communication link using USRP devices and the OpenAir interface, OAI, protocol stack. The split learning setup is also deployed here, with the first layers running on the user side using a CPU-based device, and the remaining layers on the GPU server. The terminal windows shown in the images demonstrate the real-time execution of training processes on both the user and server sides, verifying that the data is transmitted, processed, and returned correctly across the wireless channel. This slide shows the runtime setup and experimental results of our semantic inference task. On the top, we present the real-time execution environment where the CPU user device runs the front part of the neural network and communicates with the edge server. At the bottom left, we illustrate the semantic information inference accuracy across different cutting layers. As we can see, all configurations gradually converge with training, but deeper cuts like FP3 and FP4 achieve slightly higher accuracy. This confirms that although earlier cuts reduce computation on the user side, they may compromise performance, highlighting the need to balance between device efficiency and model accuracy in practical deployments. This slide presents the experimental results of our split federated learning framework under wireless communication. On the left, we show the communication data for different split layers. As expected, earlier splits like Layer 1 result in larger uplink packet sizes, since more data needs to be transmitted from the user to the server. However, packet loss remains low across all layers, indicating a stable link. On the right, we evaluate the overall time delay per batch, broken down into three components. Client computation, in blue. Edge computation, in red, and communication overhead, in green. We observe that splitting at later layers significantly increases the client-side workload, while earlier splits reduce device burden but increase communication costs. This again highlights the trade-off between communication efficiency and device computation, critical in XR applications where user devices have limited resources. Thank you all for your attention. We look forward to any questions or feedback you might have.